All right, let's do this thing. So I wanted to take some time to go over the problems that I asked you guys to do today. I know we still have problems from the other day that I haven't given you solutions to. We'll take care of that after the next 4 days. We're going to get a lot of information coming up as to what our classes should be like moving forward. So I want to kind of see what that's going to be like. And then we'll get an opportunity to go over these two PowerPoints together and make sure that we're kind of understand what's going on. So if you have questions about that one or questions about any of the stuff that we've done so far, just know that we'll have time in the next, I guess, following week after these 4 days of professional development that I have. We'll have plenty of time to go over this stuff. All right, so don't panic if there's stuff that's confusing you. We will eventually get to take care of that. But I wanted to go through the questions that I assigned today. Some conceptual questions. I think we'll get an opportunity to kind of talk about some of the stuff that went in the PowerPoint. Hopefully that'll help you guys kind of understand what's going on here, and we can move along. So the first question I asked you guys to do was question number 15, which says a system consists of two electric charges separated by 1 meter. How does the size of the electric force change when the charge and the separation distance are all doubled? Please explain. So first, I want to make sure you guys understand what the situation. Hey, buddy. What kind of situation we got. So let me just throw some random numbers here, right? And this is a problem-solving strategy that you guys can use too, right? If you're ever in a situation where it doesn't tell you what things are, a lot of times you can just kind of make up what things are and you'll be okay. So let me give you guys a little scenario. So let's say we have a charge A, right, that has, we'll call that Q1, and it has a charge of 2 coulombs, right? So Q is the variable for charge. Q stands for charge. I guess I should write that somewhere. Q is charge, and charge is measured in coulombs, right? Q1 is 2 coulombs, and 2 coulombs is really big, but we'll talk about that later. And then we have a charge B over here. We'll call that Q2. Again, Q is charge, and maybe Q2 has a charge of, 4 coulombs. All right, so Q1 and Q2, and their separation distance, right, how far apart they are, right, it says that in the problem, they are 1 meter apart. So what the problem's saying is, well, okay, if we double, where does it say? When each charge and the separation distance is doubled. So we want to double both the charges and the separation distance and compare the forces. So we know, right, if these are both positive, they would exert a force on each other, and it would be repulsive because like charges repel. So they would feel a force away from each other, right? We'll call it F for now because we don't know what that force is. But they would feel a force that's pushing them apart. We want to know, how does that force change if we take it, so we double each one of them. So A ends up with a charge of, well, if we double it, 2 doubled is 4. And B, right, we double B, that would be a charge of 8. And so we doubled both the charges, right? Q1 went from 2 to 4, Q2 went from 4 to 8. We also doubled the distance. So instead of 1 meter, we're looking at 2 meters. All right, and we want to compare the forces in this scenario. So they're still like charges, right? They're both positive. So they're still going to repel. So they're going to push each other away with a force. But we're not sure, right? How does this force, right? the force that's repulsing in the second part, how does that compare to this force? Well, if we're going to compare forces, we need to use the electric force equation, which is called Coulomb's law. Right? And Coulomb's law is electric force equals K times the absolute value of Q1 times the absolute value of Q2 divided by R squared. So electric force equals K times the absolute value of Q1 times the absolute value of Q2 divided by R squared, where Q1 and Q2 are both charges, right? Q1 is charge. That's going off the paper. Way to go. Q2 is also charge. And R is the separation, right? How far apart are they? And then K is a constant that we use for electricity stuff. K is a very specific number. It always has the same number. It is 8.99 times 10 to the 9th. Right? 8.99 times 10 to the 9th. It's always the same number. It's a constant, right? It helps us figure out electric force and things that have to do with electricity. So now that we kind of have that down, right, I want to talk about, how we can go about solving this. So we'll call this case 1 and case 2. These are the two things we're comparing. So let's do case 1 first, right? So I have two charges. I have a separation distance. I can find the electric force. So F equals K times the absolute value of Q1 times the absolute value of Q2 divided by the separation distance squared. I picked a whole bunch of numbers for that, right? I picked 2, 4, and the problem gave me 1. So this will be F equals K times the absolute value of 2 is just 2. Absolute value of 4 is just 4 divided by 1 squared. So if we do that out, right, that's some pretty easy math. We can get the force will be equal to 2 times 4 is 8, divided by 1 is 8. So we get K times 8. Now, I'm going to leave this as K times 8 because it's not easy to multiply by 8.99 times 10 to the 9th. And the other one will have K in it too, so we can just compare them that way. So for part 1, right, when they are 2 coulombs and 4 coulombs separated by a distance of 1 meter, we get a force of K times 8. So let's check the second one. All right, same equation. F equals K, absolute value Q1, absolute value Q2, divided by R squared. We'll get F equals K times the absolute value of 4 times the absolute value of 8 divided by, distance is now 2 squared. So that'll give us K times 4 times 8 is 32, I hope, divided by 4. And actually, that we could have done this easier, right? 2 squared is 4. If we have a 4 on the top and a 4 on the bottom, we could have just canceled it there. I'm not paying attention. But whatever, we did it already. So F equals 32 divided by 4 will give us 8K times 8. So what happens to the force if both charges and the separation distance are doubled? Well, we started with K times 8. We ended with K times 8. So the force doesn't change. Now, how could that be, right? The force didn't change. Well, let's talk about it just conceptually, right? If we make the charges bigger, right? So Q1 and Q2 get bigger. We increase the electric charge of our particles. What's going to happen to the force? Well, if we make the charges bigger, the force should get stronger, right? We make the charges bigger, the force should get stronger. If we spread them out, right, we move them farther away. Well, when we move things farther away, the force is going to get weaker. So changing the charges makes the force stronger. Moving them farther apart makes it weaker. And we just happen to pick a number, or doubling everything just happens to have zero effect, right? The effect of making the charges bigger cancels out with spreading them farther apart, and we get no overall impact, right? It just stays the same. All right, increasing the charge makes the force bigger, spreading them out makes the force smaller. The bigger and the smaller cancel out, and we end up with the exact same thing, k times 8 and k times 8, right? And you can think about it this way as well, right? If I change this by 2 times, and I change this by 2 times, well, 2 times 2 is 4, right? So the top has gotten 4 times bigger. If we do here, right, change the bottom by 2 times, but it's not just 2 times, it's 2 squared. Well, 2 squared is also 4. So the top got bigger by 4 times, the bottom got bigger by 4 times. If the top and bottom both get bigger by 4 times, that cancels out with those, and we end up with no real change. And that works for, like, if we tripled the charges and tripled the distance, it would cancel out. If we quadruple the charges and quadruple the distance, it'll cancel out, right? Any kind of change where everything is the same, right? We move everything at the same time, the forces will end up being equal. All right, so answer to number 15, if we double each charge and the separation, nothing happens, the force stays the same. All right, 16. What is the direction of the electric force between 2 positive charges? Now, this is kind of a easy and hard one to answer at the same time, right? The easy answer is if we have 2 positive charges, we have a like charge and a like charge. Well, how do positive and positive interact? They repel. Right, so what direction is the force between 2 positive charges? It is repulsive. Just like, no, I won't say that, that's mean. Repulsive, right? It repels everything. It's hard to be more specific than that, because right now, right, we've got 2 forces. One's in the positive direction, one's in the negative direction. So how can I say what direction the force is unless I'm being more specific, right? I can't say that the force is in the positive direction because this one's in the positive direction, but that one's in the negative direction. So they're in opposite directions. So the only way to answer that question is by saying they're repulsive. Same as if I had a positive and a negative, right? The only way to answer that, right? What direction is that force? The only way to answer it is to say attractive. Just like me, right? That's a joke. But we get force, right? It's an attractive force. And again, right, this one's positive, that one's negative, so we can't say what direction the force is necessarily, because there's 2 of them, and they're going in different directions. We could even, right, even if we have them above each other, right, positive and positive, right, they're above each other, well, now we have one that's going up and one that's going down. Still repulsive, right, they're repelling, but do we say the direction is upward, or do we say the direction is downward? We can't say, because it's both, right? So the only way you can answer this, right, what is direction of the force between 2 positive charges? We have to say repulsive, right? That's the only way we can answer that question. 17, what kind of object experiences 0 electric force? Now, the quick and easy answer is a neutral object. right? A neutral object would be anything that has a charge of 0 coulombs, right? And if we put 0 coulombs into our electric force equation, right, F equals K times the absolute value of 0 times, it doesn't even matter, Q2 divided by R squared. If there's a 0 in there, what does this come out to? It comes out to 0, right? It'll always be 0. So when we have a neutral object, right, Q equals 0, we're always going to get a force of 0. So what kind of object experiences 0 electric force? A neutral object. Now, we can be a little bit more particular because we talked about in the 19.1 chapter, PowerPoint, that there is this thing called polarization, where neutral objects can feel a force F-O-R-C-E if they have free moving electrons. Right? Neutral objects can feel a force if they have free moving electrons. So, for example, right? If we have, we'll call it a circle, and we have positive, negative, positive, negative, positive, negative, positive, negative, positive. 1, 2, 3, 4, 5. 1, 2, 3, 4. Oop, I need another negative. Negative. Right, so neutral object, it has the same amount of positives as it does negatives. So the charge is 0 coulombs. Everything's canceling out. But if we bring something that is positively charged close to it, right, we have a stick or something that's positively charged. Well, if the electrons are free moving, right, if they have free moving electrons, the negative charges are free moving, how do positive and negatives interact? Well, they attract. So all these negative charges are going to drift over towards the positive rod, and we'll end up with something that looks, right, these positives, this, where all the negatives end up in this top corner, right, and the positives just kind of stay where they are. Positives don't move, right? So only the electrons can move. So the positives stay where they are. All the electrons drift over here. Now, this half becomes negatively charged. This half becomes positively charged, right? Because all the negatives are over here. We get kind of a split down the middle where this part is negative, this part is positive. And because the negative part is closer, we get an attraction, right? So we had something that was neutral, but we can still get the object to attract to something if it has free moving electrons. If it doesn't have free moving electrons, then these electrons can't drift over there. They're stuck in place. What kind of materials don't have free moving electrons? Well, that's insulators, right? Conductors have free moving electrons. Insulators do not. Their electrons are stuck in place. So a more specific answer, right? The best answer would be a neutral insulator. Right? A neutral insulator will never feel an electric charge. A neutral conductor, right, could have something like this, have polarization happen. A neutral insulator will never have that happen. So neutral object is almost right. A neutral insulator is 100% right. force that holds electrons and nuclei together in an atom, right? We get a positive center. The nucleus, we get the electrons on the outside, zooming around. That's a very simple model, but it works. What force is there between the positive nuclei and the negative electrons? Well, that's an attractive electric force. And just like the attractive gravitational force keeps satellites orbiting around Earth, the attractive electric force keeps electrons orbiting around the center of an atom, right? What do we call forces that cause objects to move in circles? We'll test your past knowledge here. That would be a centripetal force. All right, the attractive electric force acts as a centripetal force, is able to keep the electron orbiting the nucleus. That was an easy one. I like that one. Force systems. Described below. Rank the systems in order of increasing electric force. So these ones we're just using our electric force equation to figure out what the forces are, and then we'll rank them. So we could do them one at a time here. F equals K, Q1, Q2, over R squared. So for the first, I guess we do it this way. So for A, right, let's do A first. Q1 is 1, Q2 is 2, R is 1. So we'll get K times 1 times 2 divided by 1 squared. That'll be 2 divided by 1. So we get K times 2 newtons. Again, it's not fun multiplying by K, and they're all going to have a K in them, so we don't need to worry about K. We'll just leave it in there as a variable. B. Same thing. K, Q1, Q2 over R squared gives us K times negative 2. This is the first case where our absolute value bars will do something. Times 4 divided by 3 squared. 2 times 4, right? This becomes positive because its absolute value is 8. 3 squared is 9. So we get K times 8 divided by 9. Or K times 8/9. All right. C. We could do the decimal if we wanted for that, but I don't think we're going to need to compare them. K, Q1, Q2 divided by R squared will give us 5 times negative 5. Again, absolute value bars will cancel that out. Divided by 5 squared, we'll get K times 25 divided by 25. 25 on the top, 25 on the bottom cancel, and we get K times 1. 1K. We could throw newtons after all these, right? They're all forces. Newtons, newtons. And last but not least, we have D. We get K, Q1. Shh, I'm teaching. Q2. I'm kidding. I don't yell at my dog all the time. R squared. This time we'll get K times 16 times 3 divided by 4 squared. I'm going to use a little shortcut here because I don't feel like doing 16 times 3. We know 4 squared is 16, so that's a 16 on the top and a 16 on the bottom. We can cancel those. that will give us K times 3 newtons. So if we're going to rank these from smallest to largest, right, because it says in order of increasing, which means we go smallest to largest, we look at these numbers. 8/9 is the smallest, 1 is next, then 2, then 3. So the ranking would go B is the smallest, so B is less than C, which is less than A, which is less than D. B, C, A, D. All right. And we got one left. 2 charges, Q and 10Q. The force exerted on Q has a size of F. Does the force exerted on charge 10Q have a size that is greater than, less than, or equal to F? Explain. So we have 2 charges. We've got one that's just Q and one that's 10 times bigger. It's 10Q, right? It doesn't say whether they're positive or negative, so let's assume they're both positive, right? So we get a repulsive force. Force pushing away. So the force on Q, the smaller one, is F, right? And we want to know, it's repulsive, so it's pushing this way. What is the force over here? How does it compare to F? Is this force bigger than F, smaller than F, or equal to F? Now, this might seem like an easy answer, might seem like a difficult question. Hopefully, it's pretty easy. If the force on Q, because of this, is F, then the force on this, because of Q, has to be F. Why is that the case, right? What is Newton's third law? Every force has an equal and opposite reaction force. Reaction. So if this charge is pushing on that charge with a force of F, then this charge has to be pushing on that charge with a force of F, right? Because of Newton's third law, every force has an equal and opposite force. Now, depending on how big they are, right? If this is a lot bigger, then what will the acceleration be like? Well, the acceleration will be a lot smaller, right? It's not going to move away as fast. This one will move away a lot faster, right? But the force has to be the same. So it is equal to F. It is not greater, it is not less, it is equal to F because they are equal and opposite reactive forces. All right, so that's what I wanted you guys to do today. Like I said, we'll see over the next 4 days what this kind of turns into. I'm sure I'll have a plan for you guys on Friday, so pay attention to your emails, pay attention to your Schoology, see what's coming up. I think I'm expected to have office hours and stuff like that, times that I'll be available for you to ask questions, so we'll get those posted as to when those are supposed to be. Other than that, like I said, just pay attention to your email, pay attention to your Schoology, make sure you're keeping an eye out for kind of how we're going to play this for the next couple days here if we're not back in school next week. All right? Take it easy.